Okay, NP-Completeness. Okay, so the goal here is to study or to identify what problems are the hardest problem in NP. Okay, because we have seen a number of problems that are in NP. As a matter of fact, those problems are actually the hardest problems in NP, the so-called NP-complete problems. So in order to prove a problem is NP-complete, we're going to need some tools. And the tools we're going to use is called polynomial time reduction. And this concept is not new, right? So when we study computabilities, we already study reduction there. The only difference here now is that the reduction has a polynomial time bound, meaning the reduction is polynomial time computable by a Turing machine. Okay, so that's the only difference. So polynomial time reduction is a reduction plus a polynomial time bound for computing that reduction. So let me write that here. Polynomial time. So sometimes we use a p time. So let me just use p time to denote polynomial time to save some writing. So p time reduction from a set A to B is, first of all, a reduction. And second is a polynomial time computable reduction. P time computable. P time computable. So then we want to say this is reduction F. And then we add many to one or mapping reduction. So this A reduction just means that this is exactly the same as the reduction we talked about before, which means that for all instance x, x is in A, if and only if f of x is in B. And this f is polynomial time computable, meaning that you have a deterministic Turing machine that on any input x, it computes f of x in polynomial time. So which means that when the machine stops, whatever you have on the output is f of x. So that's what the polynomial time reduction is. Okay, so this is not hard. So this concept is not hard. Okay, so that is the tool we are going to use to establish or to prove certain problems that are NP complete. So first we have this properties that for this reduction, which says that P is closed under polynomial time reduction. So what that means here is this. If A is reducible, or polynomial time reducible to B. Now this notation is what's in the book, what's used in the book, but in general, people would like to denote this as many one reduction in polynomial time B. Okay, if we are talking about many one reduction, or we can also talk about Turing reduction. Remember, we can also talk about Oracle Turing machines, and we can actually add a time bound to a Oracle Turing machine. Then we also have the same thing. So if A is reducible to B via a many one reduction in polynomial time or Turing reduction in polynomial time, and if B is in P, then A is in P. So what that means here is that A is not harder than B, or you can think of it as A is easier than B, okay? So that's how we use reduction to compare the difficulties of two problems from computational points of view. Okay, so proving this is straightforward because we know how to prove if A is reducible to B and B is decidable, then A is decidable, right? So we know that, but now we just add a time bound to it. So the proof is just the same proof. We just say that, okay, if B has a time bound polynomial, and since the reduction can be computed polynomial time, and the composition of two polynomials is polynomial, so then we know that if B is in P, then A is also in P. So that is not hard. Okay, so you should be able to do this yourself. Otherwise, you can just check the book. So there isn't anything that's challenge here. But okay. So now let's look at a concept called Boolean formulas in conjunctive normal form. So we know that Boolean formulas are formed on variables using logic operators. Okay, so normally we use three operators: conjunction, disjunction, and negation. So negation, sometimes we also put it on top of it. Oops. On top of, so negation X can also be written, so this is the same, bar, X bar, right? So just to make it easier to write. So what is a Boolean formula in conjunctive normal form, or CNF? Now this is same shorthand as Chomsky normal form, but Chomsky normal form is about context-free languages, about grammar. Here is about Boolean formula, even though they have the same shorthands. So we will first define what a literals are, what a literal is. Okay, so a literal. Okay, let me start a new whiteboard. Okay, so X is a variable. Then X bar or X, this is called literal. Okay, so then a clause is a set of literals connected by disjunction. Disjunctions. Okay, so we will call it C here. So that is bullet 1, bullet 2, bullet 3, and bullet 4. So a conjunctive normal form, a Boolean formula in conjunctive normal form if it is a conjunction of a number of clauses. Okay, so which means that to put this into context, we can say, let's say I have a Boolean formula with 4 variables. We can have, let's say, x1 or x2 and x1 or x2 or x3 bar and x2 bar or x4. Right, so this is a Boolean formula in conjunctive normal form. I have 3 clauses here. So this is one clause, this is another, and this is another. So we have a conjunction to connect these clauses, and each clause is a disjunction of literals. So that is this concept. We can use the Morgan laws to convert any Boolean formulas into conjunctive normal form. Okay, so that's that should be easy to be convinced. We just keep using the Morgan laws. So now let me going back to the slides here. Okay, so this is another example. It has 6 variables, 3 clauses, and this one has 6 variables. Now you have 4 clauses, and this one has a particular form in the sense that each clause has exactly 3 literals, and also they don't contain conflicting literals. So in other words, if xi and xi bar is in the same clause, then of course that clause, if it's in the same clause, then that clause is always true because xi or xi bar is always true. So that is trivial, so we don't include those trivial cases. So that means that a 3 CNF formula is a CNF formula such that each clause is non-trivial and has exactly 3 literals. And then we define 3 SAT. Did I define SAT somewhere before? Oops. Okay, so let me define SAT. So let SAT be the set of formulas. So this angle brackets again means encoding. So in other words, each formula after encoding is just a binary string. And this phi is is conjunctive normal form, and it is satisfiable. Conjunctive CNF formula. Notice. Sometimes Zoom has a lot of bugs because after a little while you cannot remove anything. Yeah, this one cannot be removed. Okay, that's SAT. So 3 SAT means that each clause has exactly 3 literals, and it's non-trivial. Okay, so it's time to take a break. So we'll come back at 8 p.m. So take a 15 minutes break. All right, so earlier we explained the concept of Boolean formulas and Boolean formulas in conjunctive normal forms, and what it means by 3 SAT and also SAT. So we now have 2 languages. One is SAT, which stands for satisfiability, not the standard SAT test, right? So this stands for Boolean satisfiability. And then the other language is 3 SAT. So these are 2 decision problems. And we know that they are both in NP, okay? Because given an instance, you just need a truth assignment. Then I can verify whether that truth assignment, under that truth assignment, that formula can be evaluated true. So that can be verified pretty easily. So these SAT and 3 SAT both in NP, and we're going to show that they are NP complete, which means that any problems in NP can be reduced to SAT, and then we're going to reduce SAT to 3 SAT. Now, reductions are transitive. Okay, so that's not hard to show. So now we are going to apply this reduction and S3, SAT, and click. So before we proving SAT and 3 SAT IMP complete, we're going to reduce, we're going to show how to reduce 3 SAT to click. Then when we show that 3 SAT is NP complete, then we know that click is also NP complete. Okay, so we first just look at, for the sake of constructing a reduction, so we get some ideas about how to construct a reduction on concrete problems. Okay, so we are no longer we are no longer use reduction to generate something that actually represents a computation history of a Turing machine. Instead, we are going to sort of like convert an instance of a given problem to an instance of another problem, so that if a instance in a given problem is positive, under this conversion or under this mapping, the instance of the other problem is also negative, positive, and vice. And if the instance of a given problem is negative, under this mapping, the instance of the other problem is also negative. So that's what this reduction really means. Okay, so now we're going to see something that's harder than what we have seen before. But this is not too hard, so we can still be managed. And gradually, when the harder ones come in, then we are going to spend more time on it. So this one we can just like we can use it as a warm-up exercise. So in order to reduce 3SAT to click, so what it really means here is that for any Boolean formula in 3S, for any instance or for any 3CNF formula, we want to know that phi is in 3SAT if and only if under this reduction F, it's in click. So what it means then is that, so we have to first interpret what it means, right? So this is what we want to show. So we got to understand what it really means so that we have a clear direction how to get there. So given a 3CNF formula, so we know that it is a disjunction. It is a conjunction of clauses, and each clause has 3 literals. And then we want to construct a graph so that graph, we're going to use nodes to represent the literals. And then we're going to use edges to represent the relationship that we can use to represent the Boolean formula, okay, in the sense of satisfiability. So that's basically what so that's the direction we want to do. So now we take a general form of this Boolean formula phi, right? So it's phi or phi. So each clause has 3 literals, so we can write them as, say, the ith clause will be AI or BI or CI. So this is the ith clause. And assuming we have k clauses, so then the general form is this. That is the general form. So then we want to construct a graph based on what is given. So a graph G is based on this formula. So I put this formula as a subscript to indicate this graph is constructed based on this given formula. And that will be part of the reduction, because reduction also would have another integer here. So this integer again depends on this Boolean formula, so I'm going to put a subscript there. So that's what we want to generate. So this reduction on a Boolean formula should return this, and that's the direction we're going to move to. So first, let's construct a graph. So So this graph here, so I have, we use, so each literal, okay, is represented by one node, okay. So each, so let me start here. So each, so we use a node to represent a literal. So that means that each literal in the formula is represented by a node in G. Is in G sub phi. And then we want to make connection, make edges between these nodes. Okay, so first, okay, just look at this part here. Okay, the three nodes within the same clause, they are not connected. Okay, so there are no edges connecting them. So that means that the edges will only cross different clauses. So that really means that if, let's say, for any clause CI, CJ, we're going to make connection AI with AJ. So we make a connection if they are non-trivial. So in other words, AJ is not negation of AI. So we make this AI BJ and AI CJ. So make these three edges if AJ is not negation of AI, BJ is not negation of AI, CJ is not negation of AI. Likewise, we can then make BI, AJ, okay, and so on. So for each node, so in other words, so you look at this sentence here. So for each node X in a triple, okay, that corresponds to a clause. And every node Y in each other triple, if Y is not a negation of X, then connect them. So that's basically what it means. Okay, so if they are not negation of each other, and you would have 3 times 3 edges, okay, 3 by 3. Of course, if some is a negation of the other, then you remove that edge. Okay, so that's how you construct this graph, G sub phi. Okay, so it's better to see an example. Okay, here it goes. Here's an example here. So I have a phi x1 or x1 or x2. So this one appears twice. And x1 bar, s2 bar, or x2 bar is the second clause. And x1 bar, s2, s2. So this appears twice. So that means now I have, so remember each node, I am going to represent one literal in a clause. So we basically just use the same names here. So what we have here is x1, x1, x2. So we got x1, x1, x2. x1 bar, x2 bar, s2 bar. So I get s1 bar, s2 bar, s3 bar. And then I get S1 bar, S2, X2. So then I put these nodes here so that they represent clauses. Okay, then there are no edges between these nodes in each triple. So this is called a triple. So the edges are cross triples. So for instance, for this triple and that triple, we'll check to see whether one is the negation of the other. If it is, you don't have an edge, otherwise you connect them. So you try X1 and X1 bar, you don't connect because X1 bar is negation of X1. But you connect X1 with X2 bar, connect X1 with X2 bar, so you got this. And then you do X1 bar, again, you don't do this, okay, but X1 bar, X2 bar, X1 bar, X2 bar, and X2 bar, you go that, you go this, and S2 bar, so because there's negation, so you don't have a connection. So that is how G sub phi is constructed. Okay, so that is a construction. Now let's see how we can use this to represent satisfiability of the given Boolean formula. Okay. And that's what this reduction means. Okay, so now the writing here is from the book, but I will just explain it slowly. So now we want to show that this is indeed a reduction. So what we need to show here is that phi is in 3SAT if and only if f of phi is in clique. Okay, so now suppose that, so this f phi, so let me write it here, or f, so this is reduction, you construct G sub phi, and this k is simply the number of clauses of phi. Okay, so this is k sub phi is the number of clauses in phi. Okay, so now we want to show. So this is what we want to show. We want to show that, so let me put it here, phi is in 3SAT if and only if this thing is in clique. Okay. All right, so now, because if and only if, that means we have two directions we need to do. So let's do the first direction, that suppose that phi is in 3SAT. That means that it has a satisfying truth assignment. Okay, so that means that at least one literal is true in every clause. Okay, so because you have k clauses and this is under one truth assignment, because it is phi is satisfiable, that under a truth assignment that makes it satisfiable, then each clause must have at least one literal that is set to true. Otherwise, you won't be able to evaluate phi to be true. Okay, so that is the first thing. I'm going to put that as the first thing. Okay, now let's look at our G sub phi. So in this graph, we know that each triple of G, we select one node corresponding to a, so in each triple of G, we're gonna select one node corresponding to a true literal. So for instance, let's go back here. Let's say in this case, x1 is true, then we're going to set this. Now, each clause, if it's satisfiable, one of them has to be at least, one literal has to be set true. You may have more than one, but there must be at least one. So we just pick one. If you have two that's set to true, then you simply pick one of those. Okay, so this is true, the other one is true, we just select them, select all of them that are true. Okay, so now for those, then you know they form a clique, they form a K-clique because, so if one variable in this, so let's say this is set true, then of course S1 is false, then this has to be set true. Okay, and oh, in this case, we don't have. Do we have a satisfiable assignment? So we say S2 true and S1. Yeah, we can. So in this way, we have to set S2 true. Okay, so this is true. So set true. So that's equal to 1. And then the X1 bar we set to be true here. And this is true. So what we are getting is that we connect the ones that are true. So we get here, here, and here. So we have a clique, 3 clique, because we have 3 clauses, so we have 3 clique, right? So I hope that this will not be too hard to see for you. Okay, so that is one direction. The other direction, so now suppose that G has a K-clique. Okay, so what does that mean? So that means that you can simply set the nodes on that clique to be true, to make each clause has a true literal, right? So this is also pretty straightforward. Okay, so so we just see, okay, suppose that G has a K-clique, then no two of the cliques nodes occur in the same triple because they don't connect each other in the same triple. Hence, each of the K triples contains exactly one of the K-cliques nodes. And we just simply set them true. So we assign true values to the variables of phi so that each literal labeling a clique node is made true. Okay, so doing so, then we can make this clause to be satisfiable. Okay, so this is, and to make the Boolean formula to be satisfiable. Okay, so this is the proof. Okay, any question? All right, so let's move on. Now we define NP-complete problems. Okay, so earlier we defined polynomial time reductions. Now we use that polynomial time reductions to define NP-complete problems. So here's the definition. A language B is NP-complete if the following two things hold true. Number one, B is in NP. Second, any other language in NP is polynomial time reducible to B. So there are two things, okay, for a problem to be NP-complete. So then the immediate result we get here is if B is NP-complete, and somehow we show that B is in P, then P is equal to NP. Okay, so that means NP is the same as P. However, after so the first NP-complete problem was identified in the early 1970s or late, I should say, in the early 1970s, 72 and 1974, separately by two computer scientists. Well, at that time, they were mathematicians, right, at that time. One was in Canada, the other one was in Moscow. They identified the first problems to be NP-complete, okay? And since then, thousands of problems have been identified NP-complete, and none of them, despite intensive efforts, have been shown to be in P. And there isn't any mathematical proof discovered yet to show they are not equal. So that means that it is open. So we don't know whether P is equal to NP. Okay, so from algorithmic point of view, we hope that it's equal, P is equal to NP, but from cryptographic point of view, we hope it's not equal because the modern cryptography depends on the notion of one-way functions. And if P is equal to NP, then no one-way functions exist. So that is two directions, right? So for cryptography, we don't want P to be equal to NP, but for algorithms, designers, we want P to be equal to NP. So, but we don't know whether it's true or not in either direction. We don't know. There isn't any mathematical proof, despite intensive efforts for about 60 years, right? Okay, but what do we believe here? Okay, so there are more people believe that P is not equal to NP than P is equal to NP. So it's widely believed. So I can only say this, right? So because there isn't any mathematical proof for this. So we are still waiting for that proof. Someone, hopefully someone someday identify that either P is prove, no, not identify, prove either P is equal to NP or the opposite. So assuming P is not equal to NP, then we have a good interpretation for this, and which actually matches our intuition, meaning finding a solution to a problem is much, much harder than simply verifying that is a solution, right? So in other words, finding is more difficult than verifying. So that's what P is not equal to NP really tells us. Okay, so that really matches our experience, right? So when you do a math problem, you're finding a solution is a lot harder. Once you find it, you can verify whether that solution is correct. So verification is a lot easier. Similarly, when you prove a mathematical theorem, finding a theorem is a lot harder, but verifying one is a lot easier. So hence your test problems was easier because you are given a proof. You just need to verify that whether that proof is correct or not. You don't need to construct a proof or find a proof, right? So that's another interpretation for this. So that is this theorem. And then the next theorem says that if B is NP-complete and B is polynomial time reducible to C, and C is in NP, then C is NP-complete. So in other words, we use the transitivity of polynomial time reduction to use existing NP-complete problem and prove new problems to be NP-complete. So that means that identifying the first set of NP-complete problems now become important because we are going to use it to prove new problems to be NP-complete. Okay, so the proof of this actually is also straightforward because if B is NP-complete, so that means any A in NP, we have A is reducible to B. Now B is reducible to C. So that means any problem A is reducible to C. So C then is NP-complete by definition. So this is really straightforward from definition. So it's not difficult. Okay. So now let's try to come up with the first set of problems that are NP-complete. So the slides I include here are not in the textbook. So in other words, I will offer a new roadmap or new route to come up with the first several problems to be NP-complete. And I believe the proofs presented here are much, much simpler than the ones you have in your book. So then from here, okay, so please just try to focus on this. You don't have this on your book. So the roadmap here is that we're going to start from halting problem because we are familiar with Turing machine halting problem. So what we need to do is just we add a time bound to it to make it a bounded halting. Then it will be a lot easier to prove a bounded halting problem to be NP-complete. But as we said earlier, that halting problem is not natural. So then we have to somehow create the natural problems. So then the first problem the first natural problem that we're going to show to be NP-complete is called bounded tiling problem, which is sort of similar to post-correspondence problem with the time bound, but now we use tiling to represent the computation history of a Turing machine. And bounded halting then was the one that proved by a Russian mathematician, as I mentioned earlier, in 1974. His name is called Leonid Levin, and he has been at BU since late 1970s. So he moved to the US after he well, it's a long story, so I'm going to skip that story. But he moved to US after he proved that result in Russia, in Moscow. And then we're going to use bounded tiling to prove SAT to be NP complete. So SAT was first proven by Stephen Cook. So he was at Toronto. And then we're going to reduce 3 SAT to, we're going to reduce SAT to 3 SAT. And that was first proven by Richard Kopp. So he was at UC Berkeley. So these will be the first set of problems that we are going to show to be NP complete. So as I'm going to present a different proof than your textbook, and I think this proof here is easier. Okay. So let's just refresh our memory what the halting problem is. So for Turing machine halting problem is this. You have a set of instances, which is a Turing machine M, and the input X to M. And this is a positive when M on X halts. Okay, so it's a halting problem. Okay, so we already showed that any problem, okay, so we can actually further show that every Turing acceptable language is reducible to H. Okay, so this is pretty straightforward. So we just let A be a Turing acceptable or recursively enumerable set. Then that means there is a Turing machine MA such that MA accepts X. So this is the definition. So we construct a reduction F by F of X being equal to MA comma X. Then of course, this F is recursive function or is computable by Turing machine. Okay, because this is simply the encoding of this Turing machine MA, and so this is straightforward. It's actually is linear time computable actually. Okay, so then F is computable. Then now we check. X is in A by definition. It means, or even only if MA accepts X, MA halts on X and accepts it. Okay, so, and so that means F of X is in H. So we can, actually we will need to do a little bit on this MA here. So we want to construct a MA prime so that on X, if it halts at an accept state, it will accept it. Otherwise, it will just loop. Okay, so that's what we did earlier. Okay, so this is so we show that H is complete. Actually, H is complete for Turing acceptable languages. Okay, so let me just put it here. So we construct a reduction MA, so be MA prime, where MA prime simulates, okay, on X, simulates MA on X, okay, and halt if MA accepts X, and loop otherwise. Okay, so that means that if MA does not accept X, then MA prime will not halt. So we do this change, and then we can, so this is really means that H is complete. Now it's not polynomial time complete, okay, just it's complete for Turing acceptable or Turing recognizable languages, or RE languages. Okay. Now, we are going to start from here because we are familiar with this H thing. So we have spent some time talking about Turing machines, talking about halting problems, and talking about how to reduce halting problems to other problems about Turing machines, right? So as we said, any problem you want to ask about Turing machine, they are not decidable because the easiest one is already not decidable, meaning that we just want to know whether this machine actually halts, right? Because if the machine computes something, it must halt first, right? So even the halting part is already difficult. Okay, so it is actually complete. So now from here, we're going to simply add a time bound. So we want to make it to be polynomial time. And then we'll come up our first NP-complete problem, which is not natural, but that's okay because we're going to start from there. So now let's look at this Boolean halting problem. So the instance now is a, because our goal here is to come up with an NP-complete problem. So we're dealing with non-deterministic Turing machine. So the instance here will be a Turing machine including non-deterministic ones, right? Because deterministic is simply a special case of non-deterministic Turing machine. So we have so this instance will be a M Turing machine, non-deterministic, and a input X. And also a time bound. So we want to include a time bound here as my input. So that means I'm going to include an integer n. Now, this is a unitary notation. So that means that this n here, 0 to the n just means integer n, so that the length of it is n itself, right? So the length of this is n. We don't want this, oops. We don't want this because if you do this, then the length of n is log n. So that is exponential. So then, of course, that will change the problems because it's no longer in NP. So that's why we use unitary notation to make sure that the problem, the boundary halting is in NP. Okay, so the question then is, does M accept X in n steps? Okay. So this n is time bound. So in other words, if we write a class and we define this by BH. So BH is a set of instances, positive instances, mx 0 to the n, where m accepts x in n steps. So then BH is NP-complete. So that is the first NP-complete problem we are going to show, and it has the easiest proof, right? Because it's about Turing machines. So actually things about Turing machine, the proofs are in general not too complicated. Well, it could get complicated, but in general, in the examples we have seen, they tend to have short proofs. Okay. Okay, so two things. Why is in NP? Well, again, you just think of, I can guess a computation path, and then I verify on that computation path is length n, and that has accept state, right? So that is in NP because the verification is can be done in polynomial time because the length of this instance is, so you have a number n because we need to find out whether your path, the path you guess has this length n, and then you check whether this m accepts x in n steps, right? Because this m is already there. So you just follow the transition function you verify on your guesses, on the guess you have, whether it actually ends at a accept state. So I already give you the proof. So now we will reduce in polynomial time every problem in NP to BH. Okay, so the proof is straightforward because we just need to add a time bound to it. Okay, so we let A be any problem in NP. Then by definition, there exists a NTM, let's call it MA, such that MA accepts A in polynomial time. So with a polynomial P, P here is a fixed polynomial with respect to MA. So the reduction we are going to construct is this. So it's MA comma X comma 0 to the P of length of X. Okay, so that is a reduction. Now we just want to verify whether this is indeed a reduction. So first we check X is in A. Now for any instance X is in A by definition, if and only if MA accepts X in P of length of X time. So that's what this means. And then this is really means that, so this is means MA comma X comma 0 to the P of length of X is in BH. That means this f of X is in BH. So this is a reduction. So that's it. So this is the easiest proof, NP-completeness proof, but unfortunately, this bounded halting is not natural because it depends on Turing machines. Okay, so the challenge was, how do we come up with the natural problems? Because then we're going to start from there to prove other natural problems to be NP-complete. And when you find it hard to come up with a polynomial time algorithm for a particular problem, it's likely that problem is NP-complete. So you first check to see whether it is in NP, and then you see whether you can reduce a known NP-complete problem to that problem, right? So the first natural problem, we call it bounded tiling. So this is first considered by Levin. First studied by Levin. So we first define what this problem is. Okay, so we know a tile is a square. We just consider a square tile. And each tile, each edge of this tile has a label. So we think of that as a color, or think of that as some kind of a symbol. It just has a label. And then you got a bunch of tiles. So each tile has a different edge label, okay? And for each type of tile, you have unlimited supplies. Okay. Okay, so this is type. Okay, so let's say A, B, C, D. Right. So each tile has these symbols on its edges. So now we are going to lay the tiles one next to each other, one next to the other. So under the condition that the common edge shared by two adjacent tiles would have the same, must have the same symbol or same label. So in other words, if I have a tile, is the first one on the right hand edge, it has color, it has a symbol A. The tile on the left, on the right, the left edge has a symbol A, then they can be put together. Likewise, if I have this, and this is B, and this is B, then I can put them. Okay, so that is how we can lay this tile. And then you are given a n by n square. Okay, so not only that, I also have a initial matched tile sequence. So this part is already matched. Then I want to see whether I can extend this partial matched tiles to cover the entire square, n by n square. So that's bounded tiling problem. The reason we call it bounded is because that your square is n by n. Now, if you remove these bounds, that's the entire space, and that is not decidable. In other words, that is complete for Turing acceptable languages. With a bounds, then it becomes NP complete. All right. So now let's look at the wording here. Instance, a finite set of tiles T, a unitary notation 0 to the n representing positive integer n as bounded Harding, and a sequence of tiles. So sequence S of tiles that match each other. So this is a partial matched tiles. And this is a horizontal, okay? This sequence is laid horizontally, is laid down horizontally. And what we want to know here is that can this partial matched tiles, horizontal sequence of tiles, be extended to tile and n by n square using tiles from T. Okay, so if you put every positive instance in a set, that will look like this. Okay, so we denote by BT the positive instances of bounded tiling. Namely, BT is a set of encodings of three things: a finite set of tile types, and an initial sequence of matched tiles in horizontal layout. And you have a unitary notation that indicates the size of your square. So what we want to know, BT contains all such instances where S can be extended to covered and n by n square using tiles from T. That's BT. And BT is NP complete. So I should call it as Levin's theorem. Okay, so in your textbook, Michael Sipser calls SAT as Cook-Turing theorem. Okay, Cook-Levin, I'm sorry, Cook-Levin theorem. But to be precise, actually, this bounded tiling should be called Levin's theorem, and SAT is Cook's theorem because they prove different things. Okay, Levin proves this, Cook proved that. But of course, from the historical point of view, they were the first NP-complete problems, natural NP-complete problems, and they were proven separately. So that was one of the reasons that Mike Sipser put them into Cook-Levin theorem. So that's a remark on your textbook. All right, so now let's see this proof. Okay, so let's see how much time do I left. So I have 20 minutes, so we should be able to finish up this proof. Okay, so first of all, BT is in NP, so it is again straightforward because what you can guess is just guess a layout of tiles and then verify whether the common edge of each pair of adjacent tiles have the same label. So verification obviously can be done in polynomial time in terms of n and t, right? And s, because s is the initial. So that's in NP, so it's straightforward. Now we're going to reduce every problem in NP to BT, okay? So the idea is similar to proving post-correspondence problem is undecidable. So in other words, we're going to use tiles to represent a computation history of a Turing machine, okay? And such that, okay, now this is important, such that I can duplicate tiles to cover the entire square, n by n square, only when the computation history ends at an accept state. If it ends at a reject state, then you cannot extend your existing tiles to cover the entire square. Okay, so that's what it means. So because we want to use tiles to represent a computation of a Turing machine, so that means that we need to construct these tiles. So now first just put things in the framework or in the setting. So we want to reduce every A in NP to BT. So because A is in NP, that means that there is a non-deterministic Turing machine, MA. Now, because we need these things, so we write it up. Finite set of states, finite set of tapes, symbols, transition function, Q0, and two halting states, accept and reject. That accepts A in polynomial time. So we will say that time is, we can say that is P. Okay. So we have this MA. And let's say on input X, it holds length of P. It holds in P of length of X steps. So now we make P a little bigger. So when that P greater than P prime of n greater than P of n. So what I want to do, we can just say this is equal to P of n plus 1. Oops. Is this? Let's make it +1. Okay, now this is important. We'll come back to this, why this is important. So then we have so this is going to be P prime of n by P prime of n. Okay. And then the sigma, the tape alphabet is 0, 1, and blank. Okay, so that's it. So that is a setting, and then we're going to construct tiles for the purpose of representing a computation history of Turing machine MA on an input X. Okay. All right, so here is the construction. So we start from the two most important ones, because the other one is just try to duplicate things. Okay, so for this one, we are going to look at a transition. So if, okay, a transition that, okay, so let me, so this just means that I am pointing, my read-write head points to alpha. My current state is Q. Okay, and then I'm going to move to the right. So that means now I put something over here. So another symbol on the right of alpha, because I want to move to the right. So this move to the right, it becomes P. And then this alpha is rewritten to beta. Then P is moved to the right. So that means that I'm going to write this configuration as beta P gamma. Okay, so now this rewrite head points to gamma, and that's the underlying state is P. So now how do I use tiles to represent this transition? Okay, so we can start from Q alpha. So that is Q alpha. And then alpha, now think about my computation. So the Turing machine computation is just on a portion of the tape, and then you change the content of the tape, change the location of the head. Then you can think of that as another portion of tape on top of it. So this is where I am, and then the next one I'm going to move up. So alpha now becomes beta. So the other one, because we move to the right, and then this gamma then becomes P gamma. And this one has to be on the right side of this tape. And then, so we can just put a P here and P here to indicate that this second one can only be placed on the right-hand side of the first one. So for each transition that looks like this, that going to the right, that change symbol from alpha to beta, I'm going to include these two tiles. Likewise, for when you move to the left, so this is where I begin with. Okay, so let me just say Q. Because you move to the left, so I'm going to include something on the left of Q. So that becomes So alpha is changed to beta, and Q moved to the left, so and become P. So basically that's what it is. So again, for this initial one, it is the same. Now let me put it down a little bit more to have some room here. So we get the same. So this is Q alpha. Alpha is changed to beta. And the next one will be gamma and then P gamma. But this thing has to be put on the left side of the first tile. So that means that I'm going to put P here and P there. So that way I can make sure this second tile can only be placed on the left-hand side of the first tile. So that's this. Okay, so we've done that already. So then for this, it just means that at a certain point, just like a post-correspondence problem, you would need to duplicate these symbols. So this for any alpha, you can just duplicate it up. Okay, and then this is important. So if you have a halting state, then you can duplicate it up only when it is a accept state, accept halting. If it's a reject halting, you can only end up there. You can no longer extend yourself, so you are there. So that means that's the reason, okay, why we want the size of the square to be P of n plus 1. Okay, so just to make sure, because at P of n step or before, you will end up at you will have to end up at a halting state because it's time bounded. So that means that in the worst case, you at this time you end up as a halting state, then you are there. So the last row you cannot extend yourself to cover it because there isn't anything that allows you to do it. Okay, so only when it's accept, then you can extend yourself. So that's what is the underlying meaning. And this part is just for your initial sequence of S. So you want to place your initial sequence. So let me erase this. You want to place your initial sequence at the lower left corner. Okay, so that is why. Okay, so at the bottom, so you can no longer put anything beneath it. So that means the bottom here, I use a dollar sign, but there isn't anything on top of it. Has a dollar sign, so nothing can be placed underneath these things. So that is the first thing. And then I want to make sure this one is the lower left tile you can replace, because that indicates that you start from this computation. So this is initial configuration Q0X. So this is X and Q0 points here. So I want to be placed into this, so then you can move up, right? Based on the tiles you have that represents or describes a computation of Turing machine. So you want to put it here. That means that I need to have a special symbol here. So this dollar sign will not be on the right-hand side of any other tile. Okay, as you see, you don't have that. But then each of these, okay, can be placed next to each other. Okay, so you look at this thing on top of it. It is the initial configuration. It can be used to represent an initial configuration. Okay, so that is the tile construction. All of those. All right. So why that the reduction works? Now let's look at the reduction. Okay. So then the desired reduction is the following. So we just constructed a set of tiles. So we are going to denote a set of tiles of T of MA because it comes from MA. It comes from its transition. Okay, and then as I said, we're going to use P of length of X. And here we make sure the original time bound is strictly less than P. So I didn't put P prime here just for the sake of writing. So initially I have, so if you look at here, so we say that MA on input X have length strictly less than P of length of X. Okay, so that's any computation path. So that's my P prime. Okay, so now we're not going to write P prime anymore. Okay, so then how do we represent the initial sequence of S? So I use these tiles. Okay, so my input, I can write my input as x1, x2, up to xn. Okay, so then my initial configuration will just be Q0x. So that will be like this. So I want the first one on the lower left corner. So that's Q0x1. And then the second one will be x2. And then the last one will be xn. Okay, and then followed by the rest of it will be filled in blank. So that's blank. Okay, so that's the initial. That's the tiles for the initial configurations. Okay, so before we start the actual verification, this is indeed a reduction. I think I better stop here. So, so you will have some time to sink it in your head. So we'll come back next week and talk about this reduction. Okay, so any question? Okay, then I'll see you next week. Bye-bye now.